All right, hello again. We're back doing the friction lab on the grass, all right? So before we had the tire on the asphalt, now we're gonna move this tire onto the grass. Now, first off, why do we care about this? Okay, where can we see this happen in real life? Well, if you're a police officer that's in charge of assessing accidents, for example, you might want to use this sort of technique to know how fast the car was going, to know who's really at fault in the accident. So if you're this police officer that arrives at the scene, and let's say that the accident got really messy. No one was hurt, everyone walked away, but it got a little messy and the car ended up in the grass. Okay, this police officer may take the tire, we'll assume that all cars have these rubber tires, and drag that tire across the grass, just like we're gonna do in our lab here. So it looks like we're hovering at around 7.5 newtons, maybe 8 newtons. Let's go with 8 newtons, okay? We can collect this data to figure out the coefficient of friction between the rubber tire and the grass. Remember, we always need two materials to have a force of friction. So if we know this coefficient of friction, then we can solve some equations and figure out what's.
And you're going to figure out in the lab what the coefficient of friction actually is.
Right.
So right now it's just something that, don't worry about it.
Spoiler alert. All right. So that first trial was with 1 kilogram, and the force of friction was 8 newtons or so. Let's go ahead and add a half kilogram for a total of 1.5, and we'll do the same experiment. There we go, now we're calibrated. All right, and with a constant velocity, it looks like we are at, let's go with 11. Let's split the difference. Let's go with 11 newtons on this one. So let's start over again. There is certainly repetition in science, but that's a good thing. You gotta be precise, right? You gotta be consistent. But now let's add another half kilogram for a total of 2. Let's run it back. And we'll see. This one's at about, oh wow.
15 and a half?
15 and a half?
15 and a half. We'll go with 15 and a half.
Yeah, let's go with that. That one was definitely fluttering around quite a bit. Have you all even seen something like this? It's called an analog, right? Not a digital type of scale. Kind of like reading a clock with numbers on it, right? This is old school. All right, I'm gonna bring it up to 2.5. 2.5. Oh, that went over.
That's all right, let's try it.
That went over. Let's see. Oh, well, that was the static friction. Okay, so now that we're moving and we're looking at kinetic friction, we're at about
19 and a half maybe?
Yeah.
Okay.
Yeah, let's go with that.
19 and a half. We'll
Let's
go
go
with
with
19
19 and a half.
And then we'll see, this may go over, but that's okay.
That's all right. You just do 20 plus. Let's go with the 3 kilograms now.
This one we're going to have some pulling music. So we're going to go with
everybody.
Don't Stop Me Now.
Because I'm having such a good time. We're doing some physics.
Don't stop me now.
And we're going strong at about 20.
22, 23, 23?
I think so.
Okay.
I think 23 is a really good
All right.
estimate.
23.
So again, plot your data, linearize your data, because I'm sure there's some error in there. And let's see what kind of relationship we've got.
All right, bye kids.